All right, so one of the things that confused me as a student, and I think confuses my students as well, is when you're integrating over a sphere in spherical coordinates. Like, I understand how to integrate in 3D, and I understand how spherical coordinate works, but I don't really know what it means to integrate around a sphere. So that's why I've created this integration sphere here. What we've got are three axes. We've got the red as our x-axis, the green as our y-axis, and the blue is our z-axis. And we've got a sphere here that's set to have a uniform function across it. So we're taking an integral over this whole thing. So I've got this integrating a uniform function over the entire sphere. So that goes from theta equals 0 to theta equals pi, and from phi equals 0 to phi equals 2 pi. You only want one of your angles to go from 0 to 2 pi, because otherwise you're double counting the sphere. And we end up with 4 pi here, which is what you expect for integrating your solid angle around a sphere. You expect to get 4 pi steradians. But what's neat about this is I can change this integration bounds, right? So I can change, let's try changing the phi first, that planar angle. So this is going to swoop around from the x-axis. So when I get up to 90 degrees, I'm taking out a quarter of the sphere. So I've only got 3/4 of the sphere there. So I should have, yep, 3/4 pi right down there. I can keep going around and get around to the other side here, get around to just about 180 degrees or pi radians. So there I've got half of a sphere. Sure enough, I've got 2 pi steradians. And this is a great way to visualize why you need these things, why you need only one angle to go from 0 to 2 pi, because otherwise you would be looping around the theta angle twice, right? So if I take theta to halfway, that needs to go here. If I had theta going around twice, then it would be a problem. Here I've got, what is that? That's a quarter of a sphere, so I should have just about pi steradians. I'm losing my accuracy there because I'm not quite at pi over 2 there. And then I can even cut this a little bit to maybe get an eighth of, oop, that's too much. I can get an eighth of a sphere. So that's kind of cool. So that's a neat visualization, I think. Of course, we want to work with more than just uniform functions. So let's go back here and change our function. So let's see. Let's try a function instead of being one that's uniform. Let's just try our function being equal to theta. So I've got t for theta, p for phi, just so I didn't have to keep, changing them over and over again. So let's run this program and see how it works. So the way I've indicated the value of the function is by the color. So blue indicates a higher value. The red down here indicates a lower value because theta is going from here down to this way. So let's see. Let's try changing our theta max here. So that's going to, that's taking off from the bottom. So this is higher, this is lower, excuse me. Oh, that's right, because it starts at 0 and goes down to pi. Okay, so I had that backwards. So as I slide this over, I'm going to get less of the sphere, and I can get an idea of how that integral changes, right? Because here, where I've got the higher value of theta, it's going to cost me a lot in terms of the integral. Whereas if I change this one, it's not going to cost me quite as much because I'm dealing with lower values of theta there. Of course, it's symmetric around the phi rotation axis. Let me try to get this all on one screen. There we go. So if for example, if I change this, it's taking out a pretty regular chunk of it, right? Because the coloration is going down along the phi angle, the theta angle. It's not going along variations in the phi angle. Let's go back over here. Let's comment this one out. Let's try doing the function equal to phi. Now this one's interesting because phi is running around from 0 to 2 pi. So it starts at 0 here, runs around to 2 pi, and it's got this weird little gluing effect right here where I suddenly drop from 2 pi back down to 0. So that's a little bit artificial. You can play around with that if you would like to. But I found it more interesting to set it up as a quadratic, phi minus pi quantity squared, because now it doesn't have that gluing effect. It's nice and symmetric going around this way. It's nice and continuous. And so this one's interesting because now theta is not the special angle anymore. It's phi that is determining the variation in the function value. So I can change my theta a bit and I get kind of equal changes as I go around. But now when I change my phi, I get a much more drastic change here near the red border than I do if I go around to the blue side. See, the integral value is not changing as much around this way, whereas when I get back closer to the 0 to 2 pi barrier, my integral is changing by a whole lot more. Let's try one more function here. Let's try an f of, let's just try combining them. Theta times phi minus pi squared. And in fact, let's even make it theta squared, just for kicks and giggles. We'll click on run. And so here I've got mostly blue. It's mostly peaking down here. So let's try changing our theta first. So let's slice off that larger value there down at the bottom. Oops, that's theta man. I keep getting this confused. Let's try slicing that theta down there off the bottom. So you see I've got a pretty drastic change in theta there. And then as I come down, or as I lower this thing down, I don't get as big of a change anymore because I've already taken off most of the function value there. Whereas if I take it off from the top, I don't get as big a change, right? I go from 122, I get to the equator, and I'm only down to 110. I've still got most of the integral to go in the lower half. Whereas if I do the same thing here with the phi value, let's start changing our phi min, I start slicing off a lot, whereas once I get around to the other side, I don't end up changing it by as much. So anyway, if you're having trouble visualizing these spherical coordinate integrals, I hope that's helpful to you. If you come up with another interesting function that's interesting to look at, do please let me know in the comments below. Thanks so much for watching. I will see you next time. Bye-bye.